Okay, so this this is a really short topic. Basically, we're talking about endothermic and exothermic chemical reactions. Since this unit is on heat, like thermochemistry, kind of talking about heat energy, we're going to kind of talk about how we can classify chemical reactions based on if they release heat energy or if they absorb heat energy. And you've probably heard of these terms before, so hopefully they're not super new. One thing to remember is like endo, right? That means in. And then exo, right? That means out. Okay, so as we're talking about whether something absorbs or releases heat, we can actually use these prefixes here, endo and exo, to help us keep track of which is which. Okay. So like we said, chemical reactions can be classified based on whether they absorb heat energy or they release heat energy. Okay. So if we had to think of endo and exo, remember our prefixes, which term do we think is going to absorb or take in energy? Right. So that's going to be our endothermic, because endo means in, right? And then releases heat, exo, outer, puts out, that's our exothermic. Okay, so just make sure you can keep track of what those words mean. So when we're talking about this heat energy is either released or absorbed, like I said, you've probably heard of those terms before, but this is actually why that needs to happen. Okay, so why is energy either released or why is it absorbed? So when we're looking at chemical reactions, right, we have these, like here's an example down here. We have some compounds, right, which is two different elements that are bonded together. Okay, we even have a diatomic element, oxygen. So inside these bonds, we actually have stored energy. Okay, remember we kind of, that bond energy graph, that graph that kind of looked really weird. Well, I probably should have drawn the X and Y first. And we talked about how the two atoms, right, they're attracted to each other. And when they reach that kind of happy point where they're, both attracted and repulsed at the same time, that kind of meeting point, right, that we call that they have a certain amount of bond energy, right? And we can measure that on our y-axis, right? This point down here where they're the least amount of energy, but there is some energy stored in those bonds, okay? And this is actually why when we eat food, right, the energy that we get from that food is actually being stored in these bonds. Okay, so as our body digests these foods, it's actually releasing the energy that's being stored in those bonds. Okay, so like in the calorimetry lab, if you burned your potato chip or your Cheeto, right, when you're burning it, that's a chemical reaction, right? Catching fire, burning is a chemical reaction. It's breaking those bonds of those food and it's releasing the energy that is stored inside those bonds. Okay, so your body does that just in a different way because obviously your body doesn't burn fire on the inside. Okay, so that's where this energy is coming from. And so we have two terms. That's our bond energy, right? The energy that's stored. So that's our stored energy. Okay, and then we have this other type of energy that we call activation energy. Basically, all reactions, whether they either end up absorbing heat or releasing heat, they all require some amount of energy just in order to break those bonds initially. So this is, make sure you kind of know activation energy is just the energy that kind of helps them break those initial bonds. Okay, so that a chemical reaction can actually take place and things can rearrange. If I don't have a little bit of activation energy to actually break that bond, then nothing's ever ever going to happen. There's never going to be any kind of reaction. Okay. So when we're saying what's actually happening to that energy being released or absorbed, okay, so we know that every reaction needs just a little spark of energy. That's why a lot of times when you want a chemical reaction to take place, like the calorimetry lab, right, we lit it on fire so that it took a little bit of energy from that match or from the heat the flame. And that's what started the whole process. Okay, so that's where it got its activation energy from. Usually that's what happens. It gets activation energy just from the heat around it, just from the outside environment. So when we're trying to say if it's either endothermic or exothermic, we're ignoring that little bit of activation energy that it took in at first, because they all do that. And then we're kind of looking at the final result. Is the overall energy at the end greater, or is it less than the beginning? Okay, so some reactions, like this is saying right here, okay, they release a lot of energy when they're forming new bonds. So like if I have a bond with, let me scroll back up here, this picture here. Okay, so let's look at this picture, and I'll kind of erase all this stuff that I have in the way. So if I'm looking at this picture right here, okay, here I have like carbon and hydrogen bonded together, okay? So when I break this bond with a little bit of activation energy, and then if I kind of scroll over to the other side, my carbon's now bonded to oxygen. Okay, so it takes a different amount of energy for carbon to bind to a different element. So over here where it's bonded to hydrogen, now it's bonded to oxygen. Okay, there's a different energy level. So it just kind of depends on what type of reaction, what's actually occurring, and the energy is going to be different. So just like what it's saying here, some reactions release a lot of energy during that formation of new bonds. So it doesn't actually take as much energy for carbon to bond to oxygen as it did for it to bond to hydrogen. Okay, that's basically what it's saying. It released a lot of energy in this whole reaction. So we could actually say down here, okay, that CH4, which is methane plus oxygen, makes water, carbon dioxide, and releases energy. Okay, this is our combustion reaction. So we've talked about those. It's been a while. This is like how your car works, right? Or a propane tank, some kind of fuel, right, is combined with oxygen. Usually you need some kind of spark or a light. That's like if you're in your car, you have a spark plug, right? So if your spark plug's bad, guess what? Your car doesn't crank. So that little spark plug does just that. It sparks the fuel so it can start burning. And you end up with water vapor, carbon dioxide, and then the reason your car actually runs is because you get a lot of energy from that reaction. Okay, so it's releasing energy. So here's a little graph, and you'll have to, some of the questions on the homework module, I'm gonna cross out quiz, homework module, or look at this graph. Okay, so let's look at our exothermic first. Okay, so we know that we have our reactants here. Okay, so we have a certain amount of energy. Okay, and then we said we need a little bit of activation energy. So that's right here. So we got to give it a little bit. So our energy is going to go up just a little bit because we have to have enough energy to actually break those bonds. However, once those bonds are broken, by their rearranging, they're going to actually release a lot of energy. So their total energy is going to drop down a lot lower than the way that it started. Okay, so I have this energy that's released is just the difference between what I started with and what I ended with. Okay, whereas if I have an endothermic reaction, right, I have my reactants right here. This is their starting amount of bond energy. Okay, and then in this case, these reactions usually, what happens is it actually takes more energy to form new bonds. So let me write that down so you can see it. So it takes energy to form bonds. Okay, so you can see the activation energy is much higher because not only does it need energy to break those initial bonds, but it actually needs energy to form the new bonds. If it isn't given enough energy, then the reaction won't actually even take place. Okay, it might start, but it's not going to actually complete the full reaction because it runs out of energy. And then you can see that it still gives off a little bit of energy here. But it's still overall needed more energy in order to form those bonds. Okay, so it needed a lot of energy to get started, right? And it didn't ever release all that energy back out. So I'm still taking in energy overall at the end of the system. Okay, so how do we know which type of reaction has taken place? Well, we can use temperature. Okay, because remember, temperature is just a measure of energy. Okay, so if I'm, let's say, this is probably going to be easiest just to draw. So let's say I have a substance here, right? And I have some kind of reaction taking place in here, right? If I am releasing energy, release energy, right? So if I'm releasing energy, that means that the kinetic energy is increasing, right? Of this environment out here. That means my temperature is going to go up. Okay. So anytime we see an increase in temperature, right? If you think of an explosion, it's hot, right? All that heat is being released to the outside environment. That is an exothermic reaction. Okay. Let me do a different color. Let's look at an endo. So let's say, right, I have a reaction taking place here. Okay. And remember, endo reactions, they need energy. So that means energy, it's going to take energy from the outside environment and put it into the reaction. So it takes energy, takes in energy. So that means that in my outside environment, my kinetic energy is going down, which means my temperature has to go down. Okay, so anytime we see a decrease in temperature, it's gonna be an endothermic reaction. Okay, because it's actually taken that energy and actually put it into the bonds. Okay, so that means there's less energy in the outside environment. So it's because it's taken into the bonds. Okay. And then here is, if you need to pause it to fill in the notes, this just goes over exactly what I just drew. Okay, so if you need to pause it here to write down the words, that's fine. Last but not least is just this term catalyst. So a catalyst is just something that can actually increase the rate of reaction. You'll hear this term a lot, especially if you take chemistry in college, and you've probably already heard it if you've had biology or any other science. Catalysts are talked about a whole lot, but they just increase the rate or the speed of the reaction. Okay, it doesn't mean that you're going to get more products. It doesn't mean that you're going to get less products. All it means is you're just going to get those products faster. So I'm trying to think if we didn't get to do our types of chemical reactions lab because we had already closed school, but heat is a common catalyst. There's lots of other chemicals that are common catalysts. If you watch a video like that elephant toothpaste, I didn't get a chance to do that either since we're closed, where that like the foam kind of shoots out of the bottle. Okay, that's because they add a catalyst. If you didn't add a catalyst, you would eventually have all that foam, but it wouldn't be nearly as much fun because it would just kind of very slowly overflow, and it wouldn't actually shoot up into the air like it does with the catalyst. So that's just an example. So just make sure you know what that word means. And then hopefully you should be able to complete the little homework module. I think there's only like 10 questions, and it basically just reviews a lot of these like key terms and then kind of looks at those graphs to kind of help identify, kind of read those endothermic, exothermic graphs. Okay. And just email